Hi dear students, welcome to DVMS course. Myself Sudhakar Reddy. In today's session, we are going to discuss about functional dependency and candidate keys. So let us start the session. So before going to start our actual topic, let us recall some basic definitions of mathematics, which are very useful in finding functional dependencies and candidate keys. So the first subtopic which we need is subset. As we already know this definition, let me quickly recall this. Suppose I am having two sets. Assume this is my x, y. Suppose I am having one more set which is having w, x, y, z. Okay. Now every element of A is an element of B. Every element of A is an element of B. In such cases, we say that A is a subset of B and we write it as A subset of B. Is that clear? Now, can we say A is a subset of A? Sure, why not? Because this is my A. It is having two elements. Okay, let us write to again A. It is having two elements. Now, X is an element of A, so it also belongs to A. What about Y? Y is also belongs to A. So every element of A is an element of A. So we can write A is subset of A. Is that clear? The next one is intersection. What is intersection, sir? The set of all common elements which belongs to both given sets. Suppose I am having A equal to x and y and B is equal to w, x, z. Okay. Now what are the common elements of these two sets, sir? X belongs to both of the sets. Fine. Any other elements? No. So the set of all common elements for these two sets is denoted by A intersection B. And what is the common element we are having in this example? That is x. Now suppose that I am having one more set like u, v, w. Let us consider A and C. Any common elements among A and C, sir? There is no common element. C doesn't belongs to C. X doesn't belongs to C. Y doesn't belongs to C. Similarly, any element of C is not an element of A. So the intersection of these two sets is empty. Is that clear? Now let us start functional dependencies and candidate keys. What is a functional dependency? First, let me explain what is a functional dependency with an example. Then we see what is the general definition of functional dependency. Suppose I am having a relation which consists of the attributes name, height, weight of the person and city in which he is living and pin code of that city and the state from his. Is that clear? Now, if I know the pin code of a particular person, can we say what is his city? Yes, of course. If I know the pin code, automatically I can write the corresponding city. That means if any two persons are having same pin code, they are living in the same city. So this is an example of a functional dependency. That means pin code is giving the value of city or the value of city is functionally determined by pin code. Now let me give one more example. Suppose I know a height and let us consider weight. Height and weight. Now assume that there are two persons with the same height. Now can we say the corresponding weights also same? May or may not. That means the value of weight is functionally not determined by the value of height. So this is not a functional dependency and this is a functional dependency. Is that clear, sir? So now let us see the formal definition of functional dependency. Suppose alpha is a subset of attributes the relation and beta is a subset of the relation. The functional dependency alpha goes to beta. The functional dependency alpha goes to beta holds on the relation schema are if and only if any two tuples T1 and T2 agree on the attribute alpha, then they also agree on the attribute beta. That means if there are any two tuples who are having same value of alpha, then they must also have same value of beta. Is that clear? So let us see. This is my relation schema. Assume that I am having alpha value is 1 for tuple 1 and tuple 3. If we consider the corresponding values of beta, then they must also be same. Then we say that alpha gives beta or alpha implies beta. Is that clear? So if T1 of alpha is equal to T2 of alpha, then what it will imply, sir? T1 of beta is equal to T2 of beta. Is that clear? Let us see one example. Suppose I am having a relation with two attributes A and B. Okay. Now let us verify whether the functional dependency A goes to beta holds or not. Okay. So for that what we need to do, sir? First go to the column of A and verify whether there are any two tuples which are having same value for A. If they are having same value, then go to the corresponding values of B. Verify whether they are same or not. If they are not same, surely we can say the functional dependency has failed. If they are same, then we need to verify whether there are any more tuples which are having same value for A. We need to verify all those things also. Is that clear, sir? Now come to here. In this case, tuple 1 and tuple 2 both are having 1. Both are having 1 for A. What about corresponding values of B, sir? The corresponding value of B is 4 and the corresponding value of B is 5. That means tuple 1 and tuple 2 are having same values for A, but they don't have same values for B. So this functional dependency doesn't hold. Is that clear? So let me rough this. So T1 of A is equal to T2 of A, but T1 of B is not equal to T2 of B. Is that clear? So let us verify one more functional dependency. B goes to A. So for this what we need to do? First go to the column of B. Okay, fine. Are there any tuples which are having same values? There are two tuples T3 and T4. That means I am having T3, T4. What are the corresponding values of B, sir? Both are having same value 3. Fine. Now what are the corresponding values of A? That means the right hand side. That is A is having 2 and here also A is having 2. So the values of B are same and the values of A are also same. So for this particular pair, the functional dependency holds. To say the functional dependency holds on the relation instance, I need to verify each and every possible pair where the values are equal. Now in this case, I don't have any more tuples with the same values of B. So we can say the functional dependency B goes to A holds on this particular example. Is that clear, sir? Types of functional dependency. So before going to solve more problems on functional dependency, let us see different types of functional dependency. We are mainly having three types of functional dependency. One is trivial functional dependency, and second one is non-trivial functional dependency, and third one is semi-trivial functional dependency. What is a trivial functional dependency? Whenever I am having a functional dependency x goes to y, if the right hand side y is subset of x, then we say it is a trivial functional dependency. What about non-trivial, sir? If the intersection of the left hand side and right hand side is equal to empty, then we say it is a non-trivial functional dependency. What about semi-trivial, sir? It is a combination of these two. That means the intersection is not empty and we cannot say y is a purely a subset of the left hand side. So these are the conditions of functional dependencies. What is trivial, sir? The right hand side attributes is a subset of the left hand side attributes. What about non-trivial? The intersection of left hand side and right hand side is empty. What about the last one, semi-trivial? The intersection of left hand side and right hand side is not equal to empty. So let me give some examples on these functional dependencies. Coming to the first one, can I say it is trivial? Surely. Why, sir? On right side, I am having A, which is clearly a subset of the left hand side. What about second one? On right hand side, I am having B, which is clearly a subset of the left hand side. What about the last one? On right hand side, we are having AB. So what about left hand side? We are having AB. AB itself is subset of AB. Every set is subset of itself. So I can say it is a trivial functional dependency. So let me give one more example for non-trivial. AB goes to C. What is the intersection of the left hand side and right hand side? The left hand side is A and right hand side is C. What is the intersection of these two, sir? You don't have any common elements. That means the intersection is empty. So we can say it is a non-trivial functional dependency. What about this example, sir? What is the intersection of the left hand side and right hand side? AB intersection BC, which gives, what are the common attributes, sir? That is B, which is not equal to empty. So it is an example of a semi-trivial functional dependency. Is that clear, sir? So let us continue the examples of functional dependencies so that we will get familiarity with functional dependencies. Then we start problems on candidate keys. Is that clear? So let us consider a relation which is having two attributes. One is EID and ename. That means employee ID and employee name. Is it okay? So let us verify whether this functional dependency holds on this relation or not. Can I say employee ID gives employee name? So for that, go to the column of EID. Verify whether there are any two tuples with the same value of employee ID. In this example, I don't have any two tuples which are having same values. So no need to verify anything else on right hand side. If there is no verification, everything is fine. So I can say this functional dependency holds. Is that clear, sir? What about, let us consider the next one. Ename implies EID. So the left hand side is employee name. Then go to the column of employee name. Verify whether there are any two tuples. Yes, I am having T2, T3. T2, T3. What is the employee name of these two? The employee name of these two is B. What about employee ID of the corresponding tuples? The employee ID of T2 is 2 and T3 is 3. That means they are having same values for left hand side, but they don't have same values for right hand side. So this functional dependency doesn't hold on this relation. Is that clear, sir? Now, before going to next example, can I say this functional dependency holds on this? Employee ID implies employee ID. Can we say, sir? Sure, why not? The right hand side is a subset of the left hand side. So employee ID always gives employee ID. So a trivial functional dependency always holds on any relation. Is that clear? The next example. Suppose I am having a relation with three attributes A, B, C. So let us verify some functional dependencies. The first one, A implies B. Let us verify it. Go to the column of A. Verify any two tuples which are having same values. In this case, T1 and T2. These two tuples are having same values. What are the values, sir? 1. What about the corresponding values of B, sir? The corresponding values of B are 1 and 2. That means the tuples are having same value for left hand side, but they don't have same values for right hand side. So we say this functional dependency doesn't hold on this relation instance. Is that clear, sir? So let us verify some more. Let us verify whether B implies A or not. So what we need to do? Consider the column of B. Fine. Verify any two tuples with the same values. In B, I think we are having a tuple 1 and a tuple 3. These two are having same value. What is the value, sir? 1. What is the corresponding values of these two tuples, sir? In B, for tuple 1 I am having 1 and for tuple 3 I am having 2. So that means here also the left hand side values are same but the right hand values are not same. So we say this functional dependency doesn't hold. Is that clear? The next functional dependency is A goes to C. Okay. So consider the left hand side attributes A. Verify whether there are any two tuples with same values. I think we are having T1 and T2. These two are having same values 1. What about the corresponding values of C, sir? T1, T2. These two are having 4. So that means these two tuples are having same values for A as well as C also. Then what we need to do? We should not say it holds. Then verify whether there are any more tuples with the same values of the left hand side. In this case, tuple 3 to tuple 5, tuple 3, tuple 4, tuple 5, all these are having same values for A. What about the corresponding values of C, sir? They are also having same values. So that implication holds for all the equal pairs. Then we can say this functional dependency holds on the given relation instance. Is that clear, sir? Let us take one more example. Suppose my relation is having three attributes x, y, z. Okay. Let us verify some functional dependencies. The first functional dependency we are going to verify is xz implies x. Now the question is it needed to verify this, sir? No. Why? The right hand side is clearly a subset of the left hand side. So x is a subset of xz. What does it mean? It is a trivial functional dependency. Whenever we are having a trivial functional dependency, no need to verify. It always holds on any relation instance of the given relation. Is it clear? Let us verify one more. xy implies xz. That means what I need to do? I need to go to the columns of x and y. Consider them as ordered pairs. Verify whether there are any two tuples. In these, the ordered pairs are equal. Now come to xy. When coming to xy, the first pair is 1, 4, the second pair is 1, 5, third pair is 4, 6, fourth pair is 3, 2. That means there are no two tuples which are having same values for xy. If there are no two tuples which are having same values, no need to verify. If no verification, everything will be fine. So this functional dependency holds. Is that clear, sir? So let us verify one more. xz implies y. So go to the columns of xz. Go to the columns of xz. Verify whether there are any two tuples with same values of xz. I think first tuple T1 and T3. Sorry, not T3, it is T2. T1 and T2. They are having, what are the values for xz, sir? It is 1, 3, it is 1, 3. So the two tuples are having same values for left hand side. Then what should we have? We should have same values for right hand side also. So what is the right hand side here, sir? Y. So what are the corresponding values? One is 4 and one is 5. That means the right hand side values are not same. If not same, we can say this functional dependency doesn't hold. Is that clear, sir? Now we have seen what is a functional dependency and how to verify whether a functional dependency holds on a given relation instance or not. Now let us see what are the uses of functional dependency. That means where we can use these functional dependencies. The first one is identify additional functional dependencies. When they are given some set of functional dependencies, by using some set of rules which are also called Armstrong axioms, we can identify some more functional dependencies which are holding on the given relation instance. Okay. What about next one, sir? Identify key. This is very, very important with respect to our GATE exam. So by the use of functional dependencies, we can identify what are the possible keys for a given relation instance and what are the candidate keys for the given relation. Is that clear? And identify equivalence of functional dependency sets. Whenever they are given two sets of functional dependencies, I can verify whether they are equivalent or not. What is equivalent? Any functional dependency which can be derived or which belong to the first one can be derived by the use of functional dependencies in the second one. The same can be done from second one to first one. Is that clear? So what is the next one? Minimal cover. What is minimal cover? When they given a set of functional dependencies, I can identify a set of functional dependencies with the minimum possible number of functional dependencies, but the given set of functional dependencies is equal to our minimal set of functional dependencies. That is called minimal cover. Is that clear? So in this session, what we are going to do is, we are going to learn how to identify a key and a candidate key for a given relation by the use of functional dependencies. To identify a key or a candidate key, we are having two methods. We can follow any one of these two methods. What are the methods? The first one is closure set of attributes. So first we see what is a closure set of attribute, then we see how we can use this to identify a key. And the second one is inference rules, which are also called Armstrong algorithms. So in this session, I am going to use closure set of attributes. So first I will explain what is a closure set of attributes, then I will explain how we can use this closure set in identifying keys for a given relation. Is that clear? So let us start it. Closure set of attributes. Sorry. Okay. First let me explain the procedure. What is a closure set of attributes? Suppose I am having a relation which consists of four attributes. Now consider any attribute, that may be a single attribute, or it can be two attributes, or it can be three attributes. Fine. The closure set of attributes is denoted by plus symbol. So BC plus or ABD plus. Now what is the closure set? It is the set of all possible attributes which can be derived or which can be found by the use of A. So these are all the set of all attributes which can be identified or which can be found by the use of A. Similarly BC plus and similarly ABD plus. So this is about the closure set of attributes. Then to identify the set of all derived attributes, what we can use, sir? There are two possibilities, sir. When they given a relation instance, by looking at the tuples of the relation, we can identify what are the deriving values of A, or by the use of set of functional dependencies, we can identify what are the values that can be implied by the left hand side. Is that clear, sir? Let me rough this. Okay, fine. Closure set of attributes. So this is my relation which is having 6 attributes: A, B, C, G, H, I, and they given a set of functional dependencies with let me use different color. Five functional dependencies. Fine. Now let us find closure set of some attributes. Okay. Suppose I want to find closure set of A. What are the attributes which can be derived from A, sir? A always implies A because it is a trivial functional dependency. Okay. Suppose if I am finding some BD plus, then without any second thought, what are the attributes we can write, sir? We can write B as well as D. Is that clear? Now let us see what are the other attributes which can be derived or which can be found by the use of A. Okay. By the first functional dependency, A gives B. So that means A determines B. Fine. By the use of second functional dependency, we can find the value of C. Fine. Any more attributes, sir? Yes. We already know the value of B. By fifth functional dependency, I can also identify H. Is that clear? Anything else, sir? No. So these are the 4 attributes which can be identified or which can be found by the use of A. So this is the closure set of A. What about BD plus, sir? In BD plus, we already having defaultly BD. Any more attributes, sir? By the use of fifth functional dependency, B gives H. Anything else, sir? I think no. So these are the 3 attributes which can be derived by the use of BD. So that is the closure set of BD. Is that clear, sir? Now let us find the closures of some examples. Then we go how to find candidate key and key. Assume this is my relation which is having 5 attributes A, B, C, D, E. Fine. And they given a set of functional dependencies which is having 4 functional dependencies. Fine. Okay. Now let us find the closure of A. Without any second thought, what are the things we can write, sir? We can write A in A plus, C in C plus, D in D plus. What about CD plus? I can write CD. What about AD plus? We can write AD. Now let us see what are the remaining attributes which can be derived by the use of functional dependencies. Coming to A plus, by first functional dependency, A gives B. What about anything, sir? A gives B, B gives D. That means A gives D, which is like trans 2 rule. That rules we see in the next session. So B also we can find. Anything else, sir? C, CD. No, I think we don't have anything. So this is the closure of A. What about closure of C? Closure of C trivially contains C. Anything else? C implies D, E by third functional dependency. What about anything else? Yeah, by fourth. Since we know the value of CD, I can identify AB. Is that clear, sir? What about D plus? D plus always contains D. Anything else? I think no. So the closure of D contains only D. Is that clear? Now what about CD plus? CD plus always contains CD. Fine. By fourth functional dependency, we can write AB also. We can write AB also. Anything else? A already we got, B, D. What about E? By the use of C, we can identify D and E. Is that clear? What about AD plus? With AD, I can find AD. Fine. Anything else? With A, we can find D. Sorry, with B. Anything else? No. So these are the closures of some examples. Is that clear, sir? Now let me give you one most important point. What is a key, sir? The set of attributes which uniquely determines the tuple of that corresponding relation is called a key. Is that clear? Now look at here. By the use of C, I can find the values of all the attributes of the relation. What does that mean? It is an example of a key for the given relation. Then what about here, sir? Here also, by the use of CD, I can identify the values of all the attributes. What does that mean? It is also a key. Is that clear? So if the closure of any set of attributes contains all the attributes of the relation, then it is our key. Fine. Then what is a candidate key? A key with minimum set of attributes. A key with minimal set of attributes. What does it mean? Suppose I am having a key with 3 attributes X, Y, Z. Okay. So I am having a key with 3 attributes. Fine. That means by the use of X, Y, Z, I can find the values of all the attributes. Now let us suppose that some attribute has withdrawn from this key. That means if I remove X, then it will not be a key anymore. Not only for X, sir. If I remove any attribute from the key, it will not be a key anymore. That means every attribute of the key is very important in finding the values of all the attributes. That is the candidate key. Is that clear, sir? So now let us see the procedure of finding candidate keys. For this, with respect to our exam point of view, what we do is, we are interested in minimal set of attributes. That means the candidate key should have minimum values. So for any given example, first what we do is, we find the closures of single attributes. We find the closures of single attributes. Fine. If any closure of these values contains all the attributes, then without any second thought, we can say it is a candidate key. Is that clear? Now let us suppose that in this example, I got, this is my key. Okay. So among single attributes, I got one key. Fine. What about the set of attributes with two values? So I can consider AB, I can consider AC, I can consider AD. And any other possibilities are BC, BD, CD. Is it clear? Now we need to find the closures of all these two set attributes, then three set attributes, then four set attributes. If I continue this procedure, how many values we need to find, sir? For example, if my set is having n elements, what is the number of possible subsets, sir? It is 2 power n. So it is a very big task. So let me give some shortcut to avoid some set of subsets. Okay. Now look at here. Here B is already a key. So if I add any more attributes, surely it will be a key because B can find all the values. So if I add or attach any other attributes, surely it will be a key. But it cannot be a candidate key. Why? Because the extra attribute which we added, it is waste or some extra tuple. So even if I remove, there is no loss to my key property. So that means I can say BC closure also equal to all values and BD closure also equal to all values. That means these two also can be keys. These two also can be keys. But we are interested only in candidate keys. So if they ask keys, I can say these are also keys. But if they ask for candidate keys, no need to consider these two. Why? Because the part of it or some subset of it is already a key. So it cannot be a candidate key anymore. Is that clear, sir? So we need to verify only these four. We need to verify these four. Like that, we can eliminate some set of subsets for candidate key verification. Is that clear? So let us see some examples so that we will get more understanding of candidate keys. Find out the candidate keys for the given relation and the functional dependency set. I am having a relation A, B, C, D, and these are the functional dependencies. Okay, fine. So before going to start the problems, let me give one more small trick. That is, if any attribute is not present in right side of any functional dependency, that means, for example, I am having X. This is not present in any functional dependency right side. That means it cannot be find out by the use of any attributes. That means it should be must present in our key. Is that clear? So first we need to identify whether there is any attribute which is not present on right side of any functional dependency. If it is not there, then include that in our key. If everyone is present on right side, then we follow our regular procedure. First we try single attributes, then we try two attributes, then three, then so on. Is that clear? Now coming to here, A is present on fourth. So fine. B is also present, C is also present, D is also present. So every attribute is present on right side of some functional dependency. So let us start with closures of single sets, then two sets, then three sets, like that. Okay. What is A plus R? Clearly itself contains A. What about next one? A gives B. B gives C. Then C gives D. Is that clear? So the closure of A contains all attributes of the given relation. This is an example of a key. Since it contains only one attribute, if I remove it, it will not work. I mean, it cannot be a key anymore. So it is the minimal set of attributes which is a key. So I can say it is also a candidate key. Is that clear, sir? So it is a key as well as candidate key. Then what about closure of B, sir? Closure of B contains B. Fine. Anything else? B gives C. C gives D. D gives A. So the closure of B also got all the values. So I can say it is a key. What about candidate key? Since it contains only one attribute, I can clearly say it is a candidate key. Is that clear, sir? What about C plus? C always contains C. Then C implies D, D implies A implies B. So this is also a key as well as a candidate key. What about D plus? D closure contains D itself. Anything else, sir? D gives A. Fine. A gives B. Then B gives C. So we can say this is also a key as well as candidate key. That means all single valued sets are keys and candidate keys. Now the question is whether we need to verify the sets with two attributes. Obviously no. Why? Because if I consider any two element subset, suppose I consider AB, then the part of it is already a key. So it cannot be a candidate key more. It can be a key, but it cannot be a candidate key more. But we are interested only in candidate keys. Is that clear, sir? So here I should not consider any two set which contains A. So AC, AD. All these cannot be candidate keys. Why, sir? A is already a key. What about remaining? BC, BD. What about this, sir? Whether we need to verify? No. Why? Because B already a key. What about CD, sir? C already a key, so no need to verify this. Then what about three element sets? Already two element sets are not any candidate keys. And in every three element set, we will present one of these attributes. So it cannot be a candidate keys. Is that clear, sir? So let us see one more example. Suppose I am having a relation with 6 attributes. A, B, C, D, E, F. Fine. And we are having a functional dependency with 4 functional dependencies. Fine. Clear? Now what is the first task we need to do? We need to verify whether there are any attributes which are not present on right side of any functional dependency. What about A? A is present on second functional dependency. Fine. What about B? B is present on fourth functional dependency. Fine. What about C? It is not present on right side of any functional dependency. What about D, sir? It is present on 3. What about E? It is not. What about F, sir? Yes, it is present on first functional dependency. Fine. Now I am having two attributes. I am having two attributes, C, comma, E. Okay, one second. I am having two attributes C and E. These are not present on right side of any functional dependency. That means I cannot find those values by the use of other values. So it means that what, sir? It should be part of our key. Maybe they are sufficient to find all the values of attributes, or they may not be sufficient. If they are not sufficient, we add some more attributes. If they are sufficient, it will be our key and it will be our candidate key. Let us verify this. So first we need to consider C. So find the closure of C. First I am finding the closure without adding any attributes. Why, sir? That may be extra or may not be extra. If this closure contains all attributes, why we need some extra attributes? So that's why we are considering only that one. What is the closure of C, sir? Clearly they contains C, comma, E. Fine. Anything else, sir? C gives F. Fine. Then E gives A. Fine. Then anything else? EC. EC gives D. and A gives B. Here I am having A, so I can write B. Is that clear? So the closure of CE contains all the attributes. That means it is a key. And if I remove C, I cannot find all the attributes because both are compulsory, both are mandatory. So we can say CE is a key as well as our candidate key. Now the question is whether we need to verify 3 element subsets or not. No sir. Why? If I want to write a 3 element set, we already confirmed that C and E must be present in that set. Whether it is a 3 element set or 4 element set, these two must be present. If these two must be present, it is already a key. So that means the remaining attributes are extra attributes. If I remove them, there is no loss for my key property. So these cannot be a candidate keys. That can be 3 element set, 4 element set, 5 element set. Is that clear, sir? So let us see one more example on candidate keys. I am having a relation with the 4 attributes A, B, C, D, and we are having 3 functional dependencies. A, B implies C, D, C implies A, and D implies B. Fine. Now what is the first task? Verify whether there is any attribute which is not present on right side of any functional dependency. Coming to A, it is present on 2. Fine. Coming to B, it is present on 3. Fine. Coming to C, it is present on 1. Coming to D, it is present on D. Sorry, first functional dependency. So every attribute is present on right side of some functional dependency. So what is the process? Consider 1 element sets and 2 element sets and 3 element sets, like that continue. Okay. So first let us find what is the closure of A. What is the closure of A, sir? Trivially it contains A. Anything else, sir? A not giving any values. So closure of A is A itself. What about closure of B? With the B we cannot find anything, but always it gives B, so we can write B. What about C, sir? C always gives C, and we are having one functional dependency, C gives A. Fine. And what is closure of D? It trivially contains D. Then anything else? Yeah, by third functional dependency I can find B. Anything else? No, sir. So the closure of single value attributes, they don't contain all the attributes. So all these cannot be candidate keys or keys. That means there is no key which contains only one attribute. Then what should we do? We need to identify whether there is any key with 2 attributes. So let us try each and every possibility. What are the possibilities, sir? First is AB plus. Then we try each and every one. What is AB plus, sir? Trivially we are having this time 2 attributes, sir, A and B. What about next, sir? By first functional dependency I can find D. Fine. So this is a key as well as a candidate key. Why candidate key, sir? A is not a key as well as B is not a key. That means both are compulsory for the key property. So what are the second possible 2 sets, sir? Let us try AC. AC trivially we have. Anything else, sir? C gives A, we already written. No, nothing else. So this cannot be a key. So what about next possibility? AD plus. Trivially we are having 2 attributes. One is A, one is D. Anything else, sir? Yeah. With D we can identify B. Fine. Anything else? Yeah. With AB we can find CD. Right. So this can also be a key as well as candidate key. What are the remaining possibilities, sir? BC plus. What is BC plus? Surely we will have 2 attributes, B and C. Fine. Anything else? C implies A. So we are having A. Anything else, sir? AB implies CD. So we can write C as well as D. So this is also a candidate key. Fine. What is the next possibility? BD plus. So we are having two attributes B and D. Fine. Anything else? By third one we can identify B. B is already there. No, we are unable to get any more attributes. So it cannot be a key. Fine. What is the last two sets are? CD. With CD, what are the values we can find? C and D. Fine. Anything else? Yeah, with C we can find A. With D we can find B. Again we got all attributes. So we are having, this is also a key. Is that clear, sir? So till now what are the candidate keys we got, sir? So A being, it is a candidate key, and AC, sorry, not AC, it is AD, right? AD, fine. BC, CD. So these are the candidate keys with two attributes. Now let us try for three attributes. Before trying three set attributes, we should write a set which don't have these pairs. Okay. So what about ABC? It can be avoided because AB is present. Fine. Any other possibility? ABD. This is also can be avoided because the part of it is already a key. So it cannot be a candidate key. It can be a key, sir. It cannot be a candidate key. Please remind this point. Okay. Anything else? ACD. Is it needed to verify? No. CD is already a key. So no need to verify this one. What about next one, sir? BCD. And part of it is already a key. So no need to verify. Is it clear, sir? So we are having totally how many candidate keys? 4 candidate keys for this relation. Is that clear? So this is about functional dependencies and candidate keys. Hope you all enjoyed the session. Thanks for watching. Thank you.